In this video segment, I show you how the different inverse dynamics methods that we looked at so far are nothing else than a quadratic optimization and how we can formulate this in a very generic fashion. So what we first looked at was a classical inverse dynamics method. So you're taking the bare bone dynamics equations of motion and what you're interested in, like tell me somehow how the system should move, how my Q double dot should look like, and I will identify the torque that I have to send to my actuators. And then this desired acceleration that was typically formulated as a function of a task space or a task level goal objective that we want to fulfill. So for example, my end effector velocity, my end effector acceleration should be a certain level. Then I can, knowing that I have my w dot equal to my j q double dot plus j dot q dot, I can take the pseudo inversion of my j, multiply this with w dot minus j dot q dot, and I get my desired acceleration. Now what this pseudo inversion is doing is that it will find the minimal q double dot such that this task up there is fulfilled. And that's the case if we have more degrees of freedom in our q double dot or in our q than the actual task we want to fulfill. So for example, if I have a 6 degree of freedom robot arm and I only want to determine the acceleration of the linear acceleration of my end effector, so only 3 task directions. If we have more tasks that we want to fulfill, then what we actually have to control, then the q double dot is equal to the argmin of the least square optimization of the task minus this j q double dot j dot q dot. So we try to minimize the error, the least square error between the objective, what we want to achieve, and what my q's can actually achieve. The second thing we looked at was operational space control. Now in operational space control, we directly started with W desired and used that in order to determine then the torque, and then we fed this torque into our actuators. Now the question here is like, is this really the only solution? So imagine you have again like a system where you have more degrees of freedom in joint space than what you want to achieve in task space. So this W might be only 3-dimensional while my torque is 6-dimensional. So obviously this can't really be the only solution. So in fact there is also here a null space associated to that, which says I can change my torque in this null space without actually changing the acceleration at my end effector in the desired directions I want. If you analyze this a little more in detail, then you see that this null space projection matrix is given by the following formula. So it's some sort of a mass matrix weighted pseudo inversion or so. If we go now and insert into our equation here, so we know that we want to achieve this task, so we take this one. We are inserting now q double dot, which is given from here. So we solve this equation for q double dot, we insert it in here, and then we take the torque which we have derived here, insert it in here. What we end up with is the following formulation. And as you can see here, we have jm minus 1 multiplied with I, and then j transposed jm minus 1 j transposed minus 1 times jm1. So this part here essentially cancels out. So that means that tau 0 that I'm adding here has no influence on my w dot here. So if the torque is applied in this null space, there is really no acceleration that applies to my end effector. Now we can analyze this even further. we have a look at the torque that we calculate from up here. And we are now inserting this inertia property that we have derived last time. So lambda is equal to that thing. And now what we're doing is we're taking the q double dot, which we again get from this upper equation, and we're inserting this torque in here. So what we have here is m minus 1 J transposed times this lambda matrix. And this is nothing else than describing this mapping here maps W dot to Q double dot. So in other words, what we are doing here is we create a solution which is again a certain optimal solution. So it selects these Q double dots which optimize a certain criteria. And this optimization here is some sort of a mass matrix weighted pseudo-inversion. And what it does, it's essentially minimizing the energy contribution to the system. So in summary, what we have seen here is that both classic inverse dynamics or operational space control, what they is nothing else than an optimization problem that we're solving under a bunch of linear constraints. And these linear constraints are on one side the dynamics equations of motion and this linear dependency between joint and task space acceleration. So in other words, we can formulate a quadratic optimization saying that what has to hold is the dynamics equations of motion. What we also know that has to hold is that there is a linear mapping between joint and task space, and then we have a bunch of optimization criteria. So for example, what I write you here, this is nothing else than what we have seen here on top. So this optimization, these three lines that we see here, are nothing else than what we have here. So we have to ensure that the dynamics equations of motion hold. We have to ensure that there is this specific mapping between joint and task space, and we want to minimize q double dot. But instead of minimizing q double dot, one could also minimize tau or any other objective we have. And this is the beauty of it. This allows us to do a lot more than what we have seen before. What we can do here is, because what we see is two things. First, we have two parameters that we're interested in, torques and accelerations. So what we can do is we can formulate this in a stacked fashion, such that we are stacking these optimization vectors together. And we formulate this task and this task as a function of x. And then we are having an objective, which is also a function of x, and that allows you then to formulate a simple minimization function as a single task optimization or a prioritized optimization, where all the time we have here a single optimization vector that we want to find the optimal solution in order to satisfy constraints and optimize certain objectives. Before starting to dive into more detail, I want to make a small detour and give you some insight into general least square optimization. For some of you, or hopefully for most of you, this is a recap of some linear algebra that you had in your first year. So if you look at this linear equation ax minus b equal to 0, we know that we can solve for x by taking the pseudo-inversion of a and multiply with b. And what this is doing is it's minimizing ax minus b, or it's minimizing x, depending on the dimensionality or the degrees of freedom that you have in x and in the task description. Now if you have two variables, we have a variable x1 and a variable x2, but they're both again linearly coming into this constraint formulation that we're having, we can just reformulate this into a stacked formulation. So we're stacking x1 and x2, and we get then also stacked A matrix, but in the end it's the exact same formulation that you've seen before, and we can also either minimize the error or minimize the length of x. We can also have multiple objectives. So we have the same x here and here, but we have two different objectives, b1 and b2. So ax minus b1 equal to 0 and a2 times x minus b2 equal to 0. And also here we can write this or bring this to matrix form if we have an equal priority. We just stack the A matrices, take the pseudo-inversion times the stack of the B vectors, and you get X. And this again does the same minimization we've seen before. Or we can do it in a hierarchical fashion. So we say we have to ensure the first constraint holds no matter what, and the second constraint has to be fulfilled as well as possible as long as the first one is not violated. So in other words, what you're doing is that you're solving the first task, then you're getting a null space here, null space projection matrix, and what you have to do now is you have to modify this x0 in order to fulfill the second task as well as possible. So this first one, if we set x0 to 0, is again like just minimizing the error or minimizing x. So also minimizing x depending on the dimensionality. We then want to fulfill the second task by changing the x0. So all we're doing is you're just inserting this x in here and we're solving for x0. And then we're substituting back into the upper formula. So if I get this x0, I can substitute in here again and I get my total x. We can also write this, of course, iteratively. And what this is doing is it's minimizing the second task as well as possible, such that I'm not changing the cost of the first task. Now, as I said, we can do this not only for 2, we can do this for n tasks. So in other words, what it boils down to is solving a set of quadratic programs. And these QPs, for the problems that we're looking at, they very often have different priorities, and they allow us to exploit the null space of higher priority tasks. If you do this for every step, we solve for every single step a QP problem which says optimize the current task while ensuring that all tasks with higher priority are not violated further. And we can formulate this iteratively. This formulation you find in the script. I also put it here for completeness. In essence, what you're doing here is for the number of tasks that you're having, you're initializing the solution, you're initializing the null space projection matrix, which obviously for the first task is identity, so you can optimize in all directions. Then you iterate through all the tasks, you solve or you create the solution of that one task, which is the objective that you want to fulfill, minus all the contributions of the x's that we already generated. You then update the total solution and you update the null space projection matrix. This null space projection matrix is always like the null space of the stacked Jacobian, of course, or stacked A matrices. Of course, you have to ensure that it does not violate any of the higher order or higher prioritized tasks. Now what you see here is a formulation which works, but it's not the best thing to do numerically. What people most of the time to do is that we just resort back to efficient implementation of numeric solvers, for example quadproc, OOQP, whatever. What they are doing is they're solving quadratic optimization problems with a quality constraint that we have seen already here. But what is also very nice that most of them also allow you to integrate inequality constraints, which means that we can not only make sure that something holds, but we can also say, for example, I want to make sure that my joint torque at joint 1 does not go beyond 50 Newton meters. So I can impose inequality constraint that only become active if necessary. So with this, we go back to the same quiz we looked at before. Again, given Q, given the equations of motion, and given the end effector position rotation Jacobians, we have a couple of questions for you to solve. You don't have to really write down the solution. All you want to see is that you write down the correct formulation. So these tasks, first goal we want you to achieve is that what is the least square minimal torque to accelerate the end effector with 1 meter per second square upwards while keeping orientation in horizontal position. So again, like this means we want to have the phi double dot and the x double dot at the end effector to stay 0. Second sub question is that we assume now that the first cylinder is blocked. Blocked means it cannot move anymore. And the question is, what is the torque for all the other joints to achieve the same motion? The third sub question, now we assume that this first cylinder has a hose rupture. A hose rupture means it cannot produce torque anymore. And the question is, can you achieve the same vertical motion we defined before? And if so, how can you achieve it? And if so, why can you achieve it?